Hello viewers, welcome to the next lecture on the MOOC course on mathematical portfolio theory. You would recall that so far we have talked certain basic aspects of modern portfolio theory, particularly the expected return and risk, which forms the two pillars of this theory. And then we talked about in the last class about the expected return and risk of a 2 and a 3 asset portfolio, and we looked at what is going to be the minimum variance portfolio. That is, we determined what are going to be the weights which will lead us to obtain the portfolio of minimum variance. And also we talked about something which is called opportunity set or feasible set, which essentially is the collection of all possible combinations of the weights resulting in different portfolios. So, in today's class we start off with a discussion on the opportunity set in the context of a portfolio comprising of n risky securities. So, we start off with n securities as an extension to the case with 2 and 3 securities. So, we begin with recalling the opportunity set, and we give a visualization of this formed from n risky securities, and these are shown in figure 1 and 2. So, let me graphically give what the opportunity set will look like. So, if we remember correctly, the opportunity set will be given not in terms of weight, but rather in terms of the expected return and risk of the portfolio obtained by that risk combination. So, we will look at two scenarios. So, one scenario I will have a graph like this, and in the second scenario I will have a graph like this, with all these dotted points representing different portfolios, and the entire thing together is what constitutes the opportunity set. So, here we will have the minimum variance portfolio, and here we have the minimum variance portfolio, and this entire set, this is the opportunity set and the opportunity set here, and both of them are for n risky securities. So, why do we have two graphs? So, the first graph is basically when short sales are not allowed. That means, all your weights have to be greater than or equal to 0. That means, Wi greater than or equal to 0 for all I. And the second case, it gives the opportunity set when short sales are allowed. So, in the first case, so basically the opportunity set in the first case, this looks like scalloped quarter moon shaped, and the second case, the opportunity set is basically behind the boundary of the opportunity set. So, that means that all the feasible portfolio in case no short sales are allowed will lie within this structure, which is a scalloped quarter moon shape, and in case short sales are allowed, that means your Wi can be any real number. It is essentially going to be the collection of all portfolios which lies beyond this particular boundary. All right. So, once you have done with the with this graphical representation, so we can make the observation that all these points that I have plotted, which are actually infinite in number, all points are called feasible investments, which includes all individual securities. That means you could have a portfolio of just one asset, that is also a legitimate portfolio in the opportunity set, and all possible combination of portfolios in general. Okay, so this brings us to Markowitz diversification, which forms the backbone of modern portfolio theory. So, Markowitz diversification involves combining. So, the way this Markowitz diversification is carried out is that it involves combining securities with less than perfect positive correlation in order to reduce the risk in the portfolio without sacrificing any of the portfolio's expected return. So, just to sort of give a greater clarity to this particular statement, what we will look at is that we said that the Markowitz diversification, what is the essence of this? It means that you are combining securities, that means you are creating portfolios out of assets with less than perfect positive correlation. So, you are going to essentially, in order to attain the benefits of diversification in the sense of Markowitz diversification, what you need to do is that you need to create a portfolio picking up assets whose returns have a correlation that was less than perfect, that means correlation coefficient of returns being strictly less than 1. And this is done in order to achieve a reduction in the risk of the overall portfolio, while retaining the characteristic of the expected return of the portfolio. All right. So, this brings us to the concept of what is known as the efficient frontier. So, efficient frontier is a part of the opportunity set with a special characteristic that make it very attractive to just pick up a portfolio that lies on the efficient frontier. So, accordingly, we start off with efficient frontier with only risky securities. So, the reason we specify risky securities is because eventually we will talk about an efficient frontier with risky securities along with risk free security. So, however, for the time being we will just focus on the portfolio of n number of risky securities. So, accordingly, we define that an efficient frontier is a portfolio that has either of the following, and I will enumerate them: more return than any other portfolio in its risk class. And what do you mean by risk class? This means that any other asset with the same variability of returns, and secondly, it has less risk than any other security with the same return. So, the first thing it means that it says that if you have for a given level of risk, that is either sigma or sigma square, the portfolio on the efficient frontier would be the one which has the highest level of return amongst all those portfolios which have an identical amount of risk, and or equivalently it could also be that you fix a level of return and you will have numerous portfolios at the given level of return, and then you pick up the one which has the least amount of risk. So, this means that maximum return given a level of risk or minimum risk given a level of return, or simply the minimum variance portfolio. So, let us revisit this graphically. So, graphically again you look at the sigma ER diagram, and then we look at the opportunity set. So, remember that this entire thing is the opportunity set, and I am looking at the case where short sales are allowed. Then the efficient frontier is going to be this part of the opportunity set. So, this is what is going to be the efficient frontier. So, the reason this is the efficient frontier is the following, that if we have a certain level of risk, say I fix a sigma here, then at this level of risk there are so many different infinitely many possible combinations of portfolios at that level of risk, and among them I choose the one with the highest amount of return which lies on this line. Or equivalently, if I choose a given level of return, then what I get is that at that given level of return there are so many portfolios with different level of risk, and amongst them I will essentially choose the portfolio that has the minimum risk. So, it is the collection of such points which give the highest return for a given level of risk, or which give the minimum level of risk for a given level of return. The collection of all these points is what is known as the efficient frontier, and note that this will also include the minimum variance portfolio which is at the tip of the border. So, it is basically the part of the border of the opportunity set which satisfies these two conditions. So, now we state the efficient frontier theorem. So, the optimal portfolio for a risk averse investor will be located on the efficient frontier. So, essentially for a risk averse investor who obviously are driven by the two considerations that are enumerated in the definition of efficient frontier, for them the optimal portfolio is going to be a portfolio that lies somewhere on the efficient frontier, which will be driven by, and the particular optimal portfolio will be driven by the level of their risk appetite, that means the level of risk that they are willing to take. Okay. Now, let us look at what are going to be the efficient portfolios. Now that we have got the efficient frontier, so this is basically a collection of an extremely large number of portfolios, that means combinations of weights W1 through Wn resulting in those particular values of expected return and risk. And so, the next thing to do is that to figure out what is going to be those weights, such that those weights constituting the portfolio will end up giving you the expected return and risk lying on the efficient frontier, and these are what we are going to call as the efficient portfolios. So, efficient portfolios with only risky assets. So, remember we are still considering in the paradigm of risky assets. We now consider the problem of construction of a portfolio on the efficient frontier for portfolios with n risky assets. Accordingly, we need to consider the problem of minimization of the portfolio variance sigma p square for a given level of expected return ERP. So, this basically means that it is the minimization of the portfolio variance given a level of expected return. So, it is this problem that where I fix the expected return and then amongst all the portfolios at that expected return, I will try to obtain this portfolio which gives me the minimum risk for that given level of return, so that I get the weights of the portfolios on the efficient frontier. So, for a given level of expected return ERP. So, in other words, so we can now formulate the problem in more concise terms. So, in other words, the problem involves determination of weights that minimizes the portfolio variance. That is minimum of sigma p square, and this is nothing but minimum of, you would recall that it is summation I is equal to 1 to n, j is equal to 1 to n, w I w j into sigma I j. And this of course has to be subject to the following two constraints, namely, so the obvious constraint is the sum of the weights equal to 1, which you have seen previously, and we now have a new constraint that the given level of expected return is fixed to be ERP. So, accordingly this will be summation W I E of R I, that is the expected return of the portfolio. This is going to be equal to E of R P, that is pre-specified. Okay, so note that, just to make an observation, that in this setup the way this problem has been formulated in terms of the minimization of this function and this constraint. So, in this setup, short selling, that is negative weights are allowed. So, now let us look at these two constraints. So, the two constraints that we have mentioned above are referred to as what are known as Lagrangian constraints, and we therefore form the Lagrangian objective function for the risk minimization problem with two constraints as identified above. Okay, so then the problem becomes minimization of L into half double summation j is equal to 1 to n, I equal to 1 to n, j is equal to 1 to n, w I w j sigma I j plus lambda into the first constraint, or rather this second constraint, which is E of R p minus summation W I E of R I is equal to 1 to n, plus some gamma into 1 minus summation W I is equal to 1 to n. So, this is what is known as the Lagrangian. Now, observe that this Lagrangian, what it does is it accounts for the two constraints as well as the function to be minimized. The only thing you will notice that we have added a factor half here. So, that is for convenience, notational convenience, and also recognizing the fact that minimization of this expression is the same as minimization of half of this expression. So, note that the factor of half is for computational convenience. Further, lambda and gamma, remember that we have introduced two constants here. So, for this discussion I refer you to consult some calculus book on method of Lagrange multipliers. So, here lambda and gamma are called Lagrange multipliers. Okay, now we need the minimization of this L. So, for minimization, we set that del L del W I is equal to 0 for I equal to 1 through n, as well as del L del lambda equal to 0 and del L del gamma is going to be equal to 0. So, this gives us the following set of equations. So, del L del omega 1, this will be del L del W 1, this is going to be W 1 sigma 1 1 plus W 2 sigma 1 2 all the way to W n sigma 1 n minus lambda E R 1 minus gamma is going to be equal to 0. Likewise, del n del W n, this is going to be W 1 sigma n 1 plus W 2 sigma n 2 all the way to W n sigma n n minus lambda E of R n minus gamma is equal to 0, plus the two additional conditions that del L del lambda, this is W 1 E R 1 all the way to W n E R n minus E R p is equal to 0, and this basically recovers the constraint that we had here. So, it recovers this constraint, and you will see that the second derivative condition in terms of gamma will recover this condition. Okay, so, then del L del lambda del gamma, this is going to be W 1 plus W 2 all the way to W n minus 1 is going to be equal to 0. So, this is satisfying the constraint that sum of the weights is equal to 1. Okay, so, in concise form, we have the following. We have sigma 1 1, sigma 1 2 all the way to sigma 1 n, then E R 1 and 1, then sigma 2 1, sigma 2 2 all the way to sigma 2 n, E R 2 1 all the way to sigma n 1, sigma n 2 up to sigma n n E R n 1. Then we have E R 1 E R 2 all the way to E R n 0 0, and then we have 1 1 all the way to 1 0 0. So, this is going to be into W 1 W 2 all the way to W n into minus lambda into minus gamma, and this is going to be equal to 0, 0 all the way to 0, E R P and 1. So, for example, if you take the matrix multiplication of the first row, then you obtain the first equation here, and then this row here will give you this expression here, and these last two rows here is, if you multiply them, you will basically recover this constraint and this constraint. So, what you can do now is we can write this. So, this can be written as this is a n by 2 by n by 2 matrix. So, this can be written as C, which is a n plus 2 by n plus 2 matrix, because these are n number of rows plus these 2 rows, and same thing with columns. And this vector here, this vector is going to be, let me call this as x, as the unknown vector, and which is of the size n plus 2 rows and 1 column, and this is going to be equal to the vector b. So, if C inverse exists, then we get vector x is equal to C inverse vector v. And what is vector x? This is my vector x. So, this solves for W1, W2 all the way to Wn and lambda and gamma. Okay, now let us look at the same problem in a slightly different paradigm. So, we start off with the formulation of the matrix notation. So, accordingly we introduce certain vectors. So, let W be the vector of all the weights. It's a column vector. So, this is W1 through Wn transpose. My vector E be ER1 all the way to ERN transpose, and vector 1 is 1 1 all the way to. So, it is a vector of all ones of with transpose taken. Then how will the two constraints look like? So, let us look at the first constraint, that summation Wi E of Ri, this is equal to E of Rp, and this implies, so this can be written as W vector transpose into vector E equal to E of Rp. Likewise, the other constraint, that summation Wi I is equal to 1 to n is equal to 1, this implies that W transpose into one vector, this is equal to 1. Okay, so finally, we also introduce sigma p square, which is summation I equal to 1 to n and j is equal to 1 to n, Wi Wj sigma ij, this is vector W transpose sigma W, and here this sigma is the covariance matrix. So, once I have this set up, that means the vector formulation of the constraint and the objective function here, then the problem formulation is that we minimize L, which is summation W I W j. So, double summation W I W j sigma I j. So, we again take the factor of half into W transpose sigma W. So, let me just call this L tilde. So, this such that these two constraints are satisfied. So, this will mean W transpose E is equal to E R P and W transpose vector 1, this is equal to 1. So, accordingly, we define the Lagrangian problem as minimization of L half W transpose sigma W plus lambda E R P. So, from this constraint E R P minus W transpose E plus gamma, and I will incorporate this constraint. So, this is W transpose 1. So, this actually should be 1 minus W transpose vector 1. So, for minimization, as before, we will take the derivative with respect to the vector W with respect to vector lambda and gamma, and this is sigma W minus lambda E minus gamma 1, this is equal to the vector 0. So, let me call this equation A 1, and this will be E R P minus W transpose E equal to 0. Let me call this equation B 1, and 1 minus W transpose 1 equal to 0. Let me call this C 1. All right. So, using A 1, what do we get from A 1? So, here I can solve this for W. So, W, first of all I will take sigma W is equal to lambda E plus gamma 1, and this implies that the vector W is going to be lambda, I take sigma inverse on both the sides, pre-multiplied by that. So, sigma inverse vector E plus gamma sigma inverse vector of 1. Then combining with B 1. So, what I am going to do is that I am going to replace this W in B 1 now. So, I get E of R P is equal to W transpose E, which will be the same as E transpose W, and this is going to be E transpose, I take the W from here. So, this is going to be lambda sigma inverse E plus gamma sigma inverse 1, and this is going to be lambda vector E transpose sigma inverse E plus E transpose sigma inverse 1. Again combining A 1 with C 1, what do we get? So, we carry out the same exercise with C 1 now. So, this gives me 1 is equal to W transpose 1, which is equal to 1 transpose W, which is, now what is W? Again I will make use of this expression for W. This is lambda sigma inverse E plus gamma sigma inverse 1, which is lambda into 1 transpose sigma inverse E plus gamma. So, there should be actually a gamma here. So, please make this correction, plus gamma into 1 transpose sigma inverse of 1. All right. So, we have these two expressions that if we here. Now, what we need to do is we need to solve for this for lambda and gamma. So, so we define A to be 1 transpose sigma inverse E, that means I call this to be A. I call B to be E transpose sigma inverse E, that means this quantity. I choose my C to be equal to 1 transpose sigma inverse 1. Then I can solve this equation. So, let me call this D1 and E1. So, solving D1 and E1, we get, so we are solving for lambda and gamma. So, we will get lambda is equal to C into ERP. Remember that this is the C we have defined. Also, there is one more thing I forgot to add, that is I will define D is equal to BC minus S square. So, with this notation I can solve for D1 and E1 to obtain lambda is equal to C ERP minus A over D, and we can get gamma is equal to B minus A into ERP over D. Okay, so it can be shown that this term B is greater than 0 and C is greater than 0, and as well as D, which is BC minus A square, this is also greater than 0. Okay, now let us go back to our original expression for W. This was my original expression for W. So, I substitute lambda and gamma in this expression for W to obtain the W to be C E R P minus A over D, which is your lambda into sigma inverse vector E plus B minus A E of R P over D sigma inverse 1. So, remember this was gamma and this was lambda. Now, what we do is the following. Now, we can simplify this weight W further. So, we define another set of vectors, say G. So, I will define this to be 1 over D into B sigma inverse 1 minus A sigma inverse E. So, it is basically combining this term with it is actually combining this B term B sigma inverse 1 and this term A sigma inverse E, and I call this as a vector G, and the remaining terms I will define as H. So, this will I will define as 1 over D into C sigma inverse vector E, which is this term, minus A sigma inverse 1, which is this term without the ERP. So, then this term and this term combine. So, this will become G, and this term and this term combined will become H into E of R P, and this is equal to the weight W. So, in conclusion, we can say that therefore, the expected return and variance of an efficient portfolio are E of R P is equal to W P transpose E and sigma P square is equal to W P transpose sigma W P, where this is your W P. Now, observe very carefully here, what does this term G comprise of? The term G comprises of sigma inverse 1, sigma inverse E, and again this term H comprises of sigma inverse E and sigma inverse 1. So, these are same for since these are basically related to the expected return and the covariance matrix of the entire portfolio, and this A, B, C and D are again given in terms of this expected return vector and the vector of ones and the covariance vector. or the covariance matrix. So, accordingly the G and H that we have here, these are basically going to be fixed irrespective of the portfolio that you are taking. So, and the reason I am saying this is that once you have decided to make the asset picking, you already have made up your mind as far as the composition of the portfolio is concerned in terms of the assets that you are going to include, and so that means you have essentially frozen on the vector E and the covariance matrix sigma, which does not change. So, once this is fixed, this is a known input. So, that means that any portfolio that rides on the efficient frontier will have the weights W p given by G plus H into E r p. So, the weights will simply be now a function of E r p. So, you can you can choose the different values of portfolios on the efficient frontier by choosing different values of E r p, which specifies your level of expected return that you want, but recognizing that your G and H are going to remain fixed. Okay. So, this brings us to the last theorem, which is known as the two fund separation theorem, which is basically a direct application of the efficient frontier. So, I can make the statement that all portfolios on the mean variance efficient frontier can be formed as a linear combination of any two portfolios on the efficient frontier. So, this means that if you are looking at the sigma E r diagram and this is an efficient frontier, then essentially it means that, so this part is going to be an efficient frontier. So, it says that any portfolio on this efficient frontier, say this portfolio, can be written as a linear combination of any two portfolios. So, this means that any two portfolios on the efficient frontier is able to generate the entire efficient frontier. So, accordingly, suppose that we take any two portfolios. So, let these portfolios, so let us consider these portfolios P 1 and P 2 on the efficient frontier, such that E r P 1, that is the expected return of the two portfolios, are distinct from each other. Now, let the portfolio formed by P 1 and P 2 be denoted by Q. Now, if it is formed with P 1 and P 2, then obviously there exists a constant alpha such that E of R q is going to be equal to alpha E of R P 1 plus 1 minus alpha of E R P 2. So, this means that these two portfolios of P 1 and P 2 on the efficient frontier, they can be combined to form a new portfolio Q, such that the weight of the portfolio P 1 is alpha, and consequently the weight of the portfolio P 2 is going to be 1 minus alpha. So, that means that you already have two portfolios P 1 and P 2, and then you create a new portfolio Q, which is essentially just like a two asset portfolio, or in this case it is a portfolio of just two portfolios with the respective weights being given by alpha and 1 minus alpha. Now, you can see that if you want to create any portfolio Q out of this portfolio P 1 and P 2, then you simply need to put in a weight alpha in the portfolio P 1 and a weight 1 minus alpha in the portfolio P 2. And how do you determine those alpha? and 1 minus alpha, you do it simply by setting this to be equal to E of R Q. So, you can solve this for alpha in terms of E of R Q, which is what you specify as an investor, and E of R P 1 and E of R P 2, which is already given to you. So, now we want to show that, now as I said, as a part of the efficient frontier theorem, we need that any portfolio that you are creating, the optimized portfolio is going to lie on the efficient frontier. So, all you need to do is essentially now prove that this portfolio Q will lie on the efficient frontier, and then you are done with the statement that any combination of two portfolios in the efficient frontier, P 1 and P 2 in this case, will result in a portfolio that also lies on the efficient frontier. So, which means that that is a desirable portfolio from the point of view of a risk averse investor. So, accordingly, so that means that the investment weight. So, what is going to be this particular portfolio Q? So, when I say portfolio, I have to specify the weight. So, the investment weight for portfolio Q is determined by vector W Q is equal to alpha into vector W P 1, which is the portfolio P 1, and 1 minus alpha W P 2. Now, since we began with P 1 and P 2 being on the efficient frontier, therefore, W Q is going to be what? It is going to be alpha. Now, since the P 1 is on the efficient frontier, so obviously, its the weight can be represented as G plus H into E R P 1. So, here I am basically just making use of this result here. Similarly, I will have 1 minus alpha into G plus H into E R P 2. So, I can take the G terms, and so this alpha and 1 minus alpha terms will combine to give me G, plus I will have the H term, and along with it I will have alpha E R P 1 plus 1 minus alpha E R P 2. And alpha E R P 1 plus this term, this is nothing but, as we have already made a choice, this is going to be E of R Q. So, this means that the weight of this portfolio Q is of the form G plus H into the expected value of the return of R Q. So, therefore, since it is in this particular form, thus we can conclude that the portfolio Q also lies on the efficient frontier. Alright, so this brings us to the end of this lecture. So, just to do a recap, what we did is that we looked at the problem of minimizing the variance in case of an n asset portfolio. We talked about the opportunity set and visualize this in case where no short sales are allowed and in case when short selling is allowed. And then we talked about the efficient frontier, which essentially is those cases where a portfolio at a certain, it is a portfolio which at a certain given level of return has the minimum risk, or which at a certain given level of risk has the highest expected return, or simply it is the minimum variance portfolio. And accordingly, we formulated the problem in terms of a Lagrange multiplier problem, and then we determined what those weights are going to be, and we showed that the weights that lie on this efficient frontier is a linear combination of, or a linear function of the expected return of that particular portfolio. And that as an application to this, we showed that for a rational investor, it is always reasonable to hold a portfolio on the efficient frontier, and for that you do not need to look at all the portfolios in the efficient frontier, but you can determine the weight of the portfolio. Once you have specified your given level of risk, you can basically determine the weight of the portfolio by taking an appropriate linear combination or an appropriate two portfolio in this case which is denoted by P1 and P2 to represent another portfolio lying on the efficient frontier which exactly matches your given level of expected return. So, in the next class we will start a little more elaborate discussion on this, and we will also over the course of next 1 week we will also focus on the situation where in addition to all the risky assets we can also take into account a risk free asset in my portfolio. So, this concludes our session for today. Thank you for watching.